This may be better titled Epilogue and Introspection, because we're going to do some introspection into what we have covered in the earlier parts of the course also, because we have covered a lot. And I think you should be proud of what you've learned, and hopefully you've learned the basic principles of a lot of things, which is the most important thing. Okay, there are no required readings for this lecture. That's the good part. But basically, remember, I showed you the slide in one of the earlier lectures, the major high-level goals. We wanted to understand the basics, principles, and precedents, and hopefully we covered a lot. Like virtual memory actually shows you a good chunk of that, right? We're giving you a lot of that. And based on such understanding, hopefully you've learned how a modern computer works underneath. And hopefully we've taken an approach where you can critically evaluate the trade-offs of different designs and ideas. If you've been following, you probably know that I never dismissed a single idea saying this is bad or this is good. I gave you the good side and the bad side, and then I potentially made a judgment call saying, okay, this didn't work out well in practice because of this reasons, right? Usually because of the downsides that we discussed. So all ideas have upsides and downsides, and it's really important to be able to critically analyze those upsides and downsides. And that's if we have achieved that in this course, then I'm happy, basically, because that's perhaps the most important part of the course. So your critical thinking, your critical analysis skills. And it happened to be that we apply those critical analysis skills to ideas in computer architecture and digital design in this particular course. But those skills are applicable way beyond this course. They're applicable to any aspect of life, actually. If you've got that critical thinking skills and reinforced it in this course, then I'm happy. And we've implemented principal design, a simple microprocessor with all of its idiosyncrasies, and you've done it in FPGAs with all of the FPGAs idiosyncrasies. So hopefully you learned from that exercise a lot. And hopefully you learn to systematically debug increasingly complex systems during your labs as well. And hopefully some of you have actually been developing ideas. Maybe some others have been developing ideas and they have not been vocal about it. That's perfectly fine. But hopefully this course has set the stage so that you can develop new out-of-the-box designs and solutions to problems. Remember, we started with solutions to problems in the first lecture. Computing is all about solving problems. So hopefully we've actually achieved that as well. So, I mean, again, this is a slide from the first or second lecture, I think. The focus was on basics, principles, and precedents, and how to use them to create and implement good designs. And I think over the course of 26 lectures, we've covered them. Okay, why these goals? Regardless of your future directions, hopefully these principles will be useful for you, as I said earlier, in doing many things. Whatever your path is going into the future, and you're the only one who can choose that path, of course, potentially with guidelines from other people, of course. But whatever you choose in this list over here, design better hardware, software systems, make better trade-offs in any design, solve problems better. It could be any problem. Think in parallel and think critically. Hopefully this course helped you. And as I said, the last three are the most important, perhaps. I mean, these things hopefully you understood, but the last three are the more generally applicable skills going into the future. Solving problems, thinking in parallel, and thinking critically. And we've come a long way. If you remember, we started the transistor as the building block. We now built up to virtual memory and system software mechanisms, and also security attacks, if you will, that circumvent some of those mechanisms. And then in the meantime, we covered logic design, execution models, von Neumann model, ISA, microarchitecture, many key processing paradigms that I'm going to flash in the next slide, and the memory system and the memory hierarchy. So hopefully there are three takeaways I would like to derive from here. All we covered is real and used in real systems. At some point, it was used in real systems, and it's increasingly important because a computer architecture is becoming increasingly important. Principles we covered apply broadly. I think I hammered this home. And trade-off analysis and critical thinking that you're exposed to apply even more broadly than the principles of individual discussions. Okay, and recall, I showed you this when we started the memory lectures. We're done with this part of the lecture, and this doesn't even cover the first part of the lectures, like digital design. And we covered, you're familiar with many processing paradigms right now, and there are a lot of trade-offs associated with them. Hopefully you're thinking about them. And now you're also very familiar with memory systems. We actually came a long way understanding the memory systems, which many introductory courses do not do, which is a bit sad in my opinion, because memory is the biggest bottleneck today, as you probably know. But now we are also familiar with many aspects of memory systems, and hopefully you can think of trade-offs for many different system designs and ideas. And We also covered the computer architecture from a broad perspective. Clearly, we focused on the hardware-software interface and microarchitecture and logic, but we also covered issues related to system software, languages, and algorithms through different lectures, GPU lectures, SIMD lectures. Right now in the virtual memory lecture, for example, a good chunk was system software, but caching lectures and other lectures also. So essentially, hopefully this was a learning and growth experience for you. What we saw in this lecture, in the course of 26 lectures, actually changed the world. And it endured the test of time. A lot of the ideas that we discussed actually has enabled many revolutions in computing, like machine learning revolution being one of them, right? We talked about GPUs, SIMD engines. We talked about systolic arrays. And it will be even more important going into the future. You may not all be future architects. You may choose to be, that's fine. You may not all be system designers. You may decide not to do computer science even going forward. But hopefully your development and thinking can benefit from the way we analyze the concepts, trade-offs, principles, and the critical thinking that we apply to things. And our focus was really on understanding, learning, and critical analysis, as opposed to like number crunching. I mean, some of the homework exercise, you have to do that so that you can understand and reverse engineer. But I believe all of these are agents for your growth, understanding, learning, and critical analysis. And the course was specifically constructed to activate these agents so that hopefully they're activated lifelong, because I don't think any of these end with any education level, for example. Education is continuous for lifelong, and understanding, learning, and critical analysis is really important. And hopefully you have those agents. So let me talk about what we did not cover and also look into the future a little bit. The computer architecture is very rich. There are many ideas, much creativity, many trade-offs and problems. And hopefully we've exposed you to some of them, a good chunk of them. But as scaling, performance, energy, reliability, and security issues become worse in everywhere, computer architecture will become more and more important. I mentioned this in the first lectures. Maybe at that time you didn't have the background to fully appreciate it. Maybe you may want to watch those lectures again. But now circling back to this, hopefully you understand what I mean. This is already obvious in the accelerators that are being designed. I'm going to show you a little bit more examples actually, because things happened in the last few weeks in AI ML accelerators. Hardware security issues that we've discussed, like RowHammer, things happened last week in RowHammer. Novel execution paradigms like processing in memory. I'm going to talk a little bit more about that. In fact, I'm going to assign you a review assignment related to that. So this is going to be your review assignment. Basically, this is a lecture that I recently delivered that covers some cutting edge topics in processing in memory, but more data-centric, data-aware and data-driven architecture. So again, this is not a required assignment. It's an optional assignment, but you get 1% credit for it. And hopefully you'll learn about some processing in memory issues, some cutting edge issues in processing in memory. And I would recommend doing that, but you don't have to do that if you don't want the 1% credit. But 1% credit is nice, of course, right? Okay, so that's the optional assignment. Watch the lecture and analyze it critically. And it's very similar to the first assignment that you have done, and actually all three assignments that you've done. Hopefully you'll have a critical summary with the positives and negatives and your key takeaways. And I made this due June 20th, but we can also extend it if really needed. Okay, and if you want to watch a longer version, we have lectures on memory-centric systems that I mentioned earlier, and this is the longer version. So if you prefer to actually go deeper, you can watch the longer version also, but this is not as up-to-date as that earlier one. Okay, so going forward, I think architectures for machines that we are going to increasingly rely our lives on need to be more data-centric, data-driven, and data-aware, because data is increasing in systems. I'm going to talk about this a little bit more in the second part of this. So we really need to rethink how we design architectures, because the processor-centric architectures that we have discussed in most of this course is not scaling very well, because everything is about data, and we have a huge memory problem. And we have a huge memory problem because of the way we are designing things. The processor-centric design paradigm is not working well. I'm going to talk about that. But essentially, people have been also trying to make things more intelligent, imitate neural networks, machines like this maybe, and try to create artificial intelligence. And it's not an easy task. We really need to think more about how we understand and design architectures. That's one of the reasons why it's an exciting time to be understanding, designing computing architectures. There are many challenging, exciting problems that no one has tackled or even thought about before. We're actually really scratching the surface, I think, in intelligence, for example, and how to design systems for intelligence or genomics. And all of these can have a huge impact on the world's future. If you have a huge security problem, you can have a bad impact on the world's future. If you have a completely secure system that can provide you completely good self-optimizing, self-driving system, for example, now you can have a huge impact also. And clearly, there are many drivers for change. But these applications, as we discussed in earlier lectures, as people dream, new applications, new systems will come, and they will be formed, and data will be increasing in the systems. Of course, we should really be cognizant about how sustainable and efficient we can make computing, right? And that also relates to the significant difficulties at the technology layers. There are energy problems that we're facing, reliability problems, complexity, security, scalability problems we're facing at the lower levels, as well as at the higher levels of applications that we want to, problems that we want to solve, essentially, huge problems that we want to solve. And all of them go through designing better architectures, better systems. And I think this course is very fundamental to in introducing you to how to start solving some of those problems. Okay, so as I said, this is a great time to be a computer architect because a lot of things in the system is strained. Applications are more demanding. There are many requirements. There are multiple possibly emerging technologies, many issues, and many big problems waiting to be solved. And many big innovations require computer architecture going into the future, as we have been seeing in systems. And remember, I showed you actually many interesting things are happening today in computer architecture in the first lecture, lecture 1 of this course. Now, many interesting things actually happened during the course of this course. I'm not going to cover all of them. I'm going to show you a few. This thing, for example, happened last week. I think last week. I don't know the exact date, but we have not discussed it. So far, I've shown you systolic arrays. And in the systolic array lecture, actually in the first lecture also, we talked about TPUs, saying that we will talk about systolic arrays. This is Google's tensor processing unit, and this is version 4. They released it recently. They don't have a lot of detail about it, but they want to target even bigger machine learning applications compared to TPU3, which we talked about. Computer vision, natural language processing, recommender systems, reinforcement learning that plays Go like AlphaGo. So they have specialized acceleration mechanisms in the entire system. And you can see that their computation capability is much larger, partly because they have a lot more memory also in this, which they don't disclose. Computation capability is 250 teraflops compared to 90 teraflops in TPU3, which we have seen. And per board, you can get 1 exaflops. So this is amazing. This is, of course, this is one specialized, very specialized accelerator. And you know exactly what principles it's based on, right? Systolic arrays plus very high bandwidth memory, right? And of course, the mechanisms to orchestrate the data movement between the memories and the systolic arrays. And then you can do a lot of matrix multiplications over here and achieve 250 teraflops in this particular device, right? And we have seen TPU3, that was bigger than TPU2. And we have seen TPU2, and we have seen TPU1, right? So these things we have seen, but TPU4 was introduced last week, essentially. So as we actually take this course, go through this course, things are happening. So things are advancing so fast. It didn't used to be the case, basically. In the 1990s, early 2000s, you wouldn't see a processor being introduced once a month even, or once a year, actually, right? Now things are moving much fast because we need to keep up. We need to solve the big problems. Hopefully they're doing it for a good reason, of course. I'm assuming that they're doing it for a good reason. But as I also said in the first lecture, technology is agnostic to your purpose, right? It could be used for good or bad, and hopefully we can use it for good. And this is what happened also in the last few weeks. This is Cerebus's wafer scale engine, and I've shown you before, so I'm not going to go over it. But this is also a big improvement compared to the previous wafer scale engine. And you can see that transistors are increasing, clearly. Moore's law, at least, is partially alive. I believe it's alive, and if people are going to push forward, as long as it can stay alive, it's going to stay alive. And this is one example of it, basically. And finally, this was announced actually earlier this week. This is AMD's last level 3D last level cache. Actually, we have shown this picture. This was AMD Ryzen from 2020. You can see that most of it is cache, and we said it was 32 megabytes shared cache. What they did was they added more shared cache, except they didn't put it on this die. They put it on another die that would fit on top of the processor die that we have seen, essentially. That's the idea over here. So they increased the size from 32 megabytes to 96 megabytes. So they have an additional 64 megabyte L3 cache stacked on top of the processor die. And it's connected using two silicon vias that go up 3-dimensional. And they get very high bandwidth also into this cache. Not as good as the cache that is on die, of course, but it's still quite good. But the capacity of your cache is very highly improved right now, as you can see. And this was introduced, I think, earlier this week. And you can see that these things are happening. And this is 3D stacked architectures. They're coming, as you can see. We can 3D stack different chips on top of each other. So we're not limited by the 2 dimensions anymore. I think increasingly we're going to see systems like this, and increasingly systems will be more monolithic going into the 3rd dimension. Okay, there's one question. How have they solved the problem with the heat? So that's a great question. Basically, I think I'm not sure. There's not enough description in this announcement, but yes, whenever you go 3D, there's heat and thermals, and they need to have some sort of solution, but probably we will learn more. In the end, I think there's no magic. Either you need to have a better cooling system, which I doubt that they have increased the cooling significantly, but probably maybe they have a higher power budget, etc. Right? But it remains to be seen. Very good question. But there are many, many other ideas that we're not going to talk about and that we didn't get a chance to talk about. I mentioned some of them, but we really didn't delve into the details of it. For example, self-optimizing architectures, using machine learning principles to design controllers, caches, etc. Make the architecture self-learning and self-optimizing as opposed to having heuristics that are designed by humans. Processing in memory systems. I'm going to talk about this briefly as we segue into the future. But emerging memory technologies, I introduced phase change memory a little bit, but we didn't really go into a lot of detail. Solid state disks, interconnects, which is a missing part, and many other issues over here that I'm not going to talk about. And a lot of this is covered in advanced computer architecture courses and the seminar courses that I'm going to mention later on. But a lot of the things, actually, these things were criticized in the past, right? The 3D caches, for example, saying that these are high cost, but they provide you a principled design in some way. And in a sense, they're similar to this Oculus in New York City that I used in my earlier lectures. So if you have principled designs, they may come at a cost, and they will come at a cost, but over time, the cost will amortize itself. So it's really important to think about principled designs and push forward and make our systems better and better going into the future. And we will not regret it as we do that, because we can solve more and more problems. Of course, we need to be careful and efficient while doing that. And if you go and visit Oculus, please send me pictures. I've seen many pictures from many earlier students from this course because they like some of these architectures, I think. I think anyone who goes there likes it as well. Okay, let me quickly recall some things. We talked about run-head execution in the last lecture. This is something dear to my heart, but you can actually do things like this also. So run-head execution is an idea that I developed in my PhD, and it's, I'm not going to go through the idea again. You can watch the last lecture clearly, but it's a way of getting the benefits of a large instruction window by not stalling, actually. Instead of stalling, when you get a long latency cache miss, you do pre-execution based prefetching speculatively completely so that you can parallelize cache misses, prefetch them inside the caches, and you save cycles. And clearly, this has a lot of benefit, and I'm proud of it, given that I've done my PhD on it. And it has enabled, it has been used in systems. And you can see some systems that have been using it. And we mentioned this last time, right? Prefetching and run-head execution is employed in IBM Power 6. It's employed in Denver and in some systems that are not public also, actually. But they are not going to be public for a while, I think. But basically, you can see that there's a lot of benefit to these ideas. And clearly, you can do more readings and watch more lectures about it. But my point is that you can actually come up with these ideas also. Now you have the basics. If you critically think about the problems that we really need to solve in our systems, in architectures, you can solve those problems in innovative ways, creative ways that can be adopted by real systems going into the future. And I would recommend doing that. I would recommend exploring that path, even though you're just beginning your computer science careers, since this is a bachelor's level course. It's the end of a bachelor's level course. I don't think there's anything that prevents you from doing that if you have the desire to do so. Especially right now, you have the background also to innovate potentially. Of course, you need to digest the material a little bit, and it may take some time to do the digestion. But never underestimate yourself in the sense that you can come up with big ideas that can change the world. So as I mentioned in the last lecture, I would recommend following your passion, getting good guidance while following your passion, because hopefully your passion needs to be well guided as well so that it can solve a big problem. But along the way, you need to be resilient because in all cases, you will get pushback from people who don't understand the ideas, from people who don't care about it, et cetera, et cetera. There are many reasons to push back on new ideas. And many people do that, unfortunately. Sometimes it's fortunately, sometimes it's good pushback, sometimes it's bad pushback, but don't be derailed by it. And this is an important advice that I give you based on my experience in the past, because if you get derailed, if you don't follow your passion, then you may actually lose out, and the world may lose out on the new ideas that you can develop. So you need to, I think, relentlessly follow your passion if you're passionate about something. And it's good to be passionate about something when you're trying to solve problems. And I think building infrastructure to enable your passion is good. We have done it with RowHammer, for example. We're doing it with processing in memory. We're doing it with many research that we do. So building infrastructure takes time. There's a saying that big ideas or research is 99% sweat to get the 1% pearl. So you want the pearl, which is important and which is going to change everything. And you have to give 99% sweat, 99% of the time. You can make that 99.99% if you want, which is perfectly fine, I think. So basically, I think this build infrastructure can be rephrased as work hard, because if you want to enable something big, you need to work hard. Well, of course, you need to be principled as well, but there's no big idea that's been enabled without working hard that I know of. So I think that also requires resilience, right? So be resilient, I think, is important. And I think focus on learning and scholarship. There are a lot of things people focus on these days, even in research and scientific community, that I think are essentially anti-science. The focus really should be on what have I learned, how have I advanced the state of the art and the future, and how have I contributed to the scholarship of the world collectively. Those are the only things that really, really matter for your impact. Everything else is just noise plus bureaucracy, let's say. So I think learning and scholarship is really important, and make that the compass in your careers, I would say. And in the end, I strongly believe in this, the quality of your work defines your impact, and nothing else in the end. You have to make it high quality. Of course, there needs to be a good idea, etc. And your passion needs to lead to something big, right? But in the end, it has to be high quality to have impact. If it's low quality, then maybe you should not do it in the first place, right? And I think overall, you can make a good impact on the world, assuming you have a good mindset, good goals, and good focus going into the future. And I strongly believe in this. And I think this is, it's really important for future generations also to believe in this. And I think in the end, it all boils down to this good mindset, goals, and focus. Okay, recall this versus that, right? I think all of these that I just discussed right now, I also discussed in the last lecture, kind of point out to some people who've changed the world, right? We discussed Calatrava, for example, and a key question we asked was, how was Calatrava able to design especially ski buildings? And we said, I think I didn't use the word passion over here, but passion is one of them for sure. But hard work, perseverance, dedication, etc., and a lot of other things that he has combined over decades and decades. And of course, principled design and strong understanding and commitment to fundamentals should not be understated ever. And I think, as I said, you will be exposed to and hopefully develop and enhance many of these skills in this course. And hopefully you have seen some of them. And if you do not fully appreciate it right now, but maybe you can take a look back and try to analyze what you have learned based on what we have discussed in the first couple of lectures in terms of design mindset and how to make a difference. Okay, so with that, also I would recommend going to the Calatrava buildings and enjoying them. You may find the closest buildings around the ETH and University of Zurich, for example. Okay, so let me talk a little bit about processing in memory. This is going to be also the subject of the optional assignment that you're supposed to review. So you'll see part of that over here. But I will give you another example thing that we're working on in my group. We're working on a lot of things that we're passionate about. This is one thing that I selected. Clearly, the RowHammer I talked about many times. I don't want to talk about it again. But processing in memory, we did not talk about a lot, even though I mentioned it multiple times. But this is something that we're really passionate about. And in my opinion, hopefully when I'm teaching this course next time, I will show more and more of these processing in memory systems. And maybe if I teach this course 10 years down the road, or some other course 10 years down the road, maybe we will be talking about processing in memory-based systems in a good fraction of the course. That's what we would like to hope. And that's what we would like to enable also. But you already know that data access from memory is the major performance energy bottleneck. We've seen this in many different ways. When we motivated the memory, the memory problem and when we started studying memory, I'm going to show you some of those slides again. But basically, to critically think, if we do some critical thinking, we will quickly figure out that our current design principles cause great energy waste. Why? We're basically moving data all around the system. To access some memory location, we have to go through, to operate on some data, we need to bring the data into the processor. And that's clearly costly in terms of energy. That clearly costs us performance. We tried very hard to avoid that performance loss, right? We just discussed many, many caching, prefetching mechanisms to avoid the latency of a memory access. That complicates our system greatly. We've just seen virtual memory. We've just seen all of the aspects of virtual memory tables, TLBs, TLB hierarchies, page walkers. This is just to do the translation, not even to get the data, right? This is just to do the translation to access the data. Same thing happens with data access also, basically. We build hierarchies and hierarchies to tolerate the performance loss. That caused even more energy waste. So right now we are in a vicious cycle, I will say. In this cycle, data access is causing a lot of problems to us, wasting a lot of energy. It's causing a lot of performance problems. To avoid the performance problems, we're building huge memory hierarchies, huge prefetchers, et cetera, multi-threaded engines, et cetera. They're causing even more energy waste in our system. And we cannot break out of this vicious cycle. So how do we actually break out of this vicious cycle? Well, we need to do something different. And a critical thinker would say, why don't you process the data where the data is? Don't move the data, basically. And that's the subject of processing in memory. Do not move the data. Somebody should probably call it do not move the data engine, right? And if you look at the components that I showed you earlier in this course, we talked about computation a lot. We talked about communication a little bit. We talked about memory a lot in the last lectures. But we were very computing centric throughout the course because existing systems are overwhelmingly processor centric because that's the only place you can do computation. And computing unit includes the accelerators like GPUs today, machine learning accelerators, same thing basically. Memory is far away. Computing unit is heavily optimized. All data is processed in the processor at great system cost, as we have discussed. Processor is heavily optimized, considered the master. Everything else is dumb and largely unoptimized. So the question is this the right way of building the system? And I think based on what we have seen so far and based on this questioning that I have provided to you, probably you're ready to answer no, because you have seen these slides before, right? You've seen that we talked about Dick Seitz, who designed the Alpha processor with his team and said that memory is the biggest problem we're having. We designed this processor. It's running at 1/20th almost of its peak bandwidth. It's not finishing 4 instructions per cycle. Forget about it. It's finishing 1 instruction every 5 cycles almost. So why? It's waiting for memory. You've seen this slide multiple times in run-ahead execution also, right? In prefetching. Most of the time, the processor is waiting for memory. You've seen this slide from a Google paper where they analyzed all of their data center workloads, and they basically say the same thing. Most of the time, the processor is waiting for memory. It's not just waiting for memory, it's accessing memory, it's moving data from memory, it's wasting energy also. So basically, because we have this fundamental choice in the designs that we have in systems today, everything is processor-centric. As a result, we have grossly imbalanced systems. Processing isn't done in only one place, everything else moves and stores data. This is energy inefficient, low performance, and complex. As a result, we have an overly complex and bloated processor and system overall, as we have seen in the memory hierarchy. And this is energy inefficient, low performance, and complex as well. As a result, I've shown you this picture at some point. Most of the system is dedicated to storing and moving data. We call this a computing system, but most of the time it's moving and storing data. Actually, you've seen a lot of pictures. I haven't replicated them over here, but you've seen a lot of pictures in real systems. Most of the system is cached. More than 60% of an entire die is cached. And AMD is adding, as I showed you earlier, even more cache into the system, right? That's true for all companies, not just AMD. I picked on it because they announced this 3D stack cache, right? Okay, so maybe we're doing something fundamentally not right at this point. So, okay, data movement versus computation energy. You've also seen the slide. Basically, today, a memory access consumes 2 to 3 orders of magnitude the energy of a complex addition. So does it really make sense to move the data into the processor? And we've said that 70 years ago, this was not the case. Over time, logic scaling, technology scaling helped the performance and energy of logic gates. It didn't help the energy of the interconnect and performance of the interconnect. As a result, logic gates became much more energy efficient and faster. Interconnects stayed as slow and as energy efficient as before. They scaled a little bit, but not that much. As a result, 70 years ago, a double precision floating point operation was expensive, or even just a simple add was expensive. Memory access was less expensive, but 70 years of technology scaling made memory access much more expensive. So we're still designing systems in a processor-centric way, and that's probably not a good idea going forward. And I've also given you this picture earlier. This is a study that we did together with Google a few years ago, where we analyzed important workloads like machine learning, Chrome browser, and video encoding and decoding. And we saw that more than 60% of the total system energy is spent on data movement across the system. And that's probably not a good idea. So basically, we do not want to move data. Then the question is, how do we design a system that does not move the data, that minimizes data movement? This is a paradigm shift. We want to enable computation with minimal data movement, compute where it makes sense, where data resides. It could be anywhere. It could be memory. It could be disk. It could be tape. It could be where the data is generated in a genomics engine, for example, in a genome sequence analyzer. We want to make computing architectures more data-centric. And the goal is really processing inside memory. This is one place where we can do processing. As we have talked about memory so far, memory is not active, right? It's passive. It just gives you data. Maybe it refreshes itself. Even that, it does it under the direction of a memory controller, right? But we want to shift computation here. And that's why this is a paradigm shift. We want to store our important applications, whatever you can imagine. Machine learning could be part of these, of course. And we want to query the memory, saying, memory, do this function for me. Memory does it, provides the results. Today, we don't have the capability or the interfaces to do this. There are many questions over here. How do we design the compute-capable memory and the controllers? How do we design the processor chip and the in-memory units after this? How do we design the software and hardware interface to enable this? How do we design the programming languages, compilers, and system software to enable this? How do we design our algorithms and map them to the in-memory processing substrate over here? And how do we actually think the theoretical foundations of computing? So this is an across-the-stack problem going all the way from devices that can compute, logic that can enable computation, microarchitectures that can enable computation, interfaces that can enable pushing of computation to memory, system software, languages, algorithms that can enable this. Theoretical foundations, I will also talk about this. At some point in your career, you will take a theory of computing science course, theoretical computer science course. Maybe you're taking some of it right now. And you may learn about big O notation, for example. And if you look at the theory of computing science, it's very processor-centric. It assumes that processor is the thing that processes the data. And as a result, you count operations. Big O notation is all about complexity of algorithms, analysis of algorithms. You may be taking these courses at some point, is all about counting the operations. It's not about counting data movements. It's not about the memory at all. It's really about how many operations that you do. That's it. But if memory is the most expensive thing, is that really the right way of analyzing systems? And is that really the right way of building systems going into the future? So even the theoretical foundations of computing is ingrained with a very processor-centric mindset, if you will. And going forward, that may need to change. Even theoretical foundations of computing may be critically thought so that we have a more data-centric mindset. Okay, so processing in memory actually is a very rich field today. It's not a new idea. It was proposed in late 1960s for the first time. But today it's becoming a lot more important. And because we have a lot of issues in technology, applications, everything we talk about related to the memory system. And there are two approaches to it. I'm going to very quickly talk about them. And then I'm going to show you some example research going into the future. Processing using memory is a very interesting approach. It really uses the underlying memory substrate to do analog operations. So actually processing near memory essentially puts some logic near memory. It doesn't use the memory cells themselves to do analog operations, but it's really put some logic near memory. So it's very similar to what we have today, except processors are much more tightly integrated with the memory. For example, you may have a pipeline processor near a bank. You may have a pipeline processor inside the logic layer of 3D stacked memories, as we will see, similarly to what AMD has done, for example, with some differences, of course. So basically, both processing using and near memory view memory as an accelerator. So essentially, you have some specialized or general purpose compute capability in memory. You use that compute capability. And we know how to build a lot of accelerators in our system today, right? the difference in the memory side accelerator is that it's not bottlenecked by the memory bus. It's not bottlenecked by the cache hierarchy. It has direct access to huge amounts of storage at high bandwidth, low latency, low energy. That's why this accelerator is potentially very precious. Then, of course, how do you design that accelerator? Maybe it's a general purpose core also, right? So memory is similar to a conventional accelerator. So let me give you one example from our research. Basically, we showed that you can do in-DRAM copy, zeroing, or initialization, and or not and majority operations at low cost using analog computation capability of DRAM. And the idea is, remember the rows, you activate rows, just like in RowHammer. If you activate 3 rows concurrently, you perform computation, analog computation, which leads to bitwise AND or not and majority functions, which are functionally complete, as you know from this course, which means that you can map any program onto the substrate like you can do in DRAM. And we showed that you can actually have significant performance energy improvements, 30 to 74x in this paper. If you're interested, you can take a look, of course. And new memory technologies enable even more opportunities. These are memory technologies like phase change memory, memristors, etc., because they actually are non-volatile. As a result, the data movement is even less. So if you want to know more about this, certainly you can read the papers we have written on this topic. This is a more recent paper that has a good DRAM background also, actually, that I mentioned earlier. And this is one of the more recent papers that we've written on this topic. You can see that the paper is titled SIMDRAM, concepts that you learned in this course. Basically, we can do bit serial SIMD processing using DRAM in this particular work. Okay, there are other very exciting things that you can do in DRAM or memories in general. For example, you can generate physical unclonable functions, signatures in memory. I'm not going to talk about how you do that, but these are important for security of systems, clearly. If you have in-memory computation, you should have security substrates over there on the memory side as well. You can do true random number generation in DRAM, and this is one paper that we've written on this topic. Another paper is coming up next week. It's already on archive, actually. You can take a look. So certainly you can do a lot of interesting things inside the memory chip, just using the analog operational principles of memory without adding any logic. Okay, but there's another opportunity that you can exploit, which is the 3D stack logic plus memory, which AMD exploited in their caches, for example. And the idea over here is you have memory layers, and then you have a logic layer, and then you put memory layers on top of a logic layer, and you have 3 silicon vias to connect them, just like in the AMD processor earlier. Now you have reasonably tight integration between memory and logic. The good thing is the memory and logic is fabricated in different ways. As a result, the logic can be good quality also, but there are a lot of technology issues over here. Going forward, there are monolithic or true 3-dimensional technologies that are under development. But now you can put anything into this logic layer. Any idea that we have discussed, any processor organization that we've discussed in this course can be inside the logic layer. Now you're very close to memory, right? This is processing near memory, basically. And we have also done a lot of work in this area. We're still doing work I'm going to show you, but this is one example of the work. I'm not going to go into the details of it, but this is an accelerator for graph processing. Graph processing is very important in many applications like genomics, machine learning, etc. today. And we can actually accelerate graph processing using a processing in memory engine, near memory engine that looks like this here. Here we have one memory plus logic chip. And inside it, we have many in-order cores over here. And you don't move the data here. You basically move the computation to the data. Basically, whenever you want to update a graph node, for example, you ship the computation to the graph node that is housed by the particular memory layer that's on top of a core. So you partition your data within this 3D stack system. And of course, to scale up, you certainly need to have many of these systems interconnected, many of these chips interconnected with each other. And you can essentially do the computation across them with minimal movement of data. And with whenever you want to update something, you basically ship the function to the computation. So essentially, function to the data, sorry. So communication, essentially, this is very much like a distributed systems programming, remote function call-based programming, and hardware supports that remote function-based call-based programming. And there's prefetching mechanisms internally so that you can exploit the high memory bandwidth that you have over here. So this is beautiful, I think. It basically shows that you can do computation near memory, and you can change your programming model to enable that computation. And the benefits are significant. So when we evaluated this system in 2015, it's right now relatively old, but a lot of work has built on the system, actually. And people have shown even better results than us right now because they optimize the system. You can see that these are existing systems. What do they have in common? In common, memory and processor are different from each other. There's a dichotomy between memory and processor. Processor is here, memories are here. That's the difference. These are different types of memories, hybrid memory cube, DDR3, different types of memories. And the bandwidth is limited. Why? Because you're going off chip to go to the memory. Tesseract, which is our system that I showed you in the earlier picture, looks different. Basically, there's no dichotomy between processor and memory because they're tightly integrated with each other. Each of these is a 3D stacked chip with memory and logic in it. And the overall bandwidth that's exposed to 512 in-order cores, just like here, is 8 terabytes per second. It's more than an order of magnitude compared to the best system that we had at the time. And the benefits are commensurate. Basically, on 5 important graph processing algorithms, the performance improvement you get is more than 13x, according to our results, even without optimizing the system. And the energy improvement, and because you can exploit very high levels of memory bandwidth, and the energy improvement is also commensurate, it's more than 8x. Basically, there's significant improvement. And other later works actually show that you can increase this performance improvement with better system management, new ideas, to almost 100x on graph processing. And the energy reduction is also commensurate, which is about 100x. I don't know the exact numbers, but it's close to 2 orders of magnitude, essentially. And if you're interested, this is a work that has had a lot of influence in the field. This is not the first work on 3D stacked memory, but this is the first work that showed that you can get high speed ups by customizing a processing in memory system for graph processing acceleration, essentially. And clearly there's more work after this because it's 2015, right? So one of the important questions that we tackle is how do you enable adoption of processing in memory? Because you built this new hardware, and this is a new execution paradigm. Adoption is always an issue, right? As we discussed in this course, and as you're very well aware, whenever you change the interface, whenever you change something that has to change the software, you will have difficult adoption issues. And many people failed in the past. Even big companies like Intel, for example, whenever they wanted to change the instruction set architecture to something completely different, they couldn't because software base needed to move and they had competition. Maybe if software base needed to move was the only thing and they didn't have competition, then they could have succeeded potentially, right? By causing a lot of pain to all of the software programs in the world, but they did have competition. So it's very hard to move the software base by changing the system completely. So processing in memory is a different way of thinking about how to design systems. It's a different computing paradigm. So it always have it as adoption issues. So there are adoption issues that we tackle, like what is the functionality that you want to put? What are the applications? What are the software? What is the software like for processing in memory? How do you ease programming? How do you provide compiler and hardware support interfaces? How do you provide system support like coherence and virtual memory? These become issues in processing in memory as well. It becomes even worse in processing in memory, actually, both of them. Runtime and compilation systems. How do you design such systems to make life easier for the programmer? Data mapping, access and sharing control, protection, scheduling, etc. Everything that needs to be rethought for data-centric systems like processing in memory. And how do you design infrastructures to understand the benefits and feasibility and develop all of this? So there are a lot of questions here. And I think all of them need to be tackled, and we're tackling them. Multiple other people are tackling them. And all of them need to be solved with a change of mindset, because the benefits of enabling a processing in memory system is huge. You get significant performance and energy improvements. Your systems become more sustainable going into the future. And you basically don't violate the balanced design principle. Remember, we talked about microarchitecture design principles, critical path principle, balanced design principle, bread and butter principle. Processor-centric designs actually violate almost all of them. Maybe critical path, you can argue, but certainly bread and butter. Common operations like memory accesses are handled terribly in a processor-centric system. That's the bread and butter design, optimized for the common case. Remember the microarchitecture design principles. Balanced system design principle is destroyed in a processor-centric system because the system is not balanced. Everything just stays idle or just serves the processor, and that's it, right? So basically, we're violating a lot of principles, and we need to change our mindset so that we actually have much better and much more principled designs going into the future. So basically, we need to revisit the entire stack if you want to change the computing paradigm to a more data-centric paradigm, and we can get there step by step. So this is a huge challenge and opportunity for the future. How do we design computing architectures with minimal data movement, which will lead to fundamentally energy-efficient architectures, and that requires data-centric designs, and also fundamentally high-performance architectures, because that also requires data-centric designs. Okay, so the talk I mentioned, Intelligent Architectures for Intelligent Memory, that you are welcome to review for 1% credit is going to be about this in a little bit more detail. But if you want to learn more about processing in memory, we've written this survey paper, an overview paper that describes processing in memory. That also gives you a lot of history about why things are different today in enabling processing in memory. So if you're interested, you can actually read about this as well, or watch the longer talks that I mentioned. And there are other review papers that we have written that focus on different aspects of processing in memory. This was, for example, published in IBM Journal of Research and Development in their special issue for hardware for artificial intelligence. It's already appeared, actually. It's this stale wording over here. But you can also take a look at these other papers. And as I mentioned in earlier lectures, processing in memory systems are real right now. They're real systems. This is one example of a real system, UpMem system. It's a company in Grenoble, France, very close to Switzerland. And we work with them quite a bit, actually. And what they've done is essentially in a DRAM chip, they've added processors. And what does this mean? They call it DPUs, DRAM processing units. And now you know the internal organization of a DRAM chip. You have multiple banks, right? Here in each bank, you have a processor. I'm going to show you a picture of it in a little bit. In each bank, you have a general purpose processor with a 14-stage pipeline, I believe, if I remember correctly. And you can execute code on it. So essentially, this is an example of processing near memory. You basically have a processor near memory that you can offload code to. And you can program these systems. We have programmed these systems in our lab. And I'm going to show you a paper that you can read if you're interested. But these are real memory modules right now, very similar to your other memory modules, except these are processing capable memory modules. And I think this is fascinating. This was introduced in 2019, and you can read a lot more about their performance analysis right now. And you can see the newer version, P21 version, you can see that it has more chips. DPUs are faster. You can see one of the disadvantages of putting a DPU or processing unit inside a DRAM chip. As I said, DRAM is fabricated very differently from processing logic. It's really optimized for low leakage for the capacitor. And this goes against designing very fast transistors. And you can see this in the frequencies of the DRAM processing units that they have. Fundamentally, they're limited to smaller frequencies because inside the DRAM fabrication process, it's very, very difficult to get a 4 gigahertz processor, let alone 4. I mean, maybe not even 1 gigahertz processor, right? So it remains to be seen. But the good thing is people are trying. So the benefit comes from not high frequency design over here. The benefit comes from the fact that processor is tightly coupled with memory. You're not moving data off the DRAM chip. As a result, you're doing processing right where data is. You're saving energy, you're saving latency, you're saving performance, you're saving a lot of things. And you can do this in parallel across all of the banks. This actually has 2,560 processors if in a 40 rank system. So basically, you have a lot of capability for processing, assuming you can map your application and data nicely to the system. The benefit you're getting is not from frequency here. So you need to change the mindset also when you actually think about how to program these systems and how to take advantage of them. The benefit really comes from minimizing the data movements. And this is another maybe more beautiful picture, if you will, that is in a paper that I'm going to reference next. It basically shows that this UPMEM system in action, if you will. It has PIM-enabled memory. It also has DRAM. And PIM-enabled memory is hopefully where you offload a lot of your computation so that you don't move data between CPU and either PIM-enabled memory and DRAM. And you can see that this has 20 memory modules of 16 chips each. There are 40 ranks in total. Now you know all this terminology, hopefully. And overall, there are 2,560 DPUs. So it's a highly parallel system. It's a highly distributed system within a node, as you can see over here. And you need to program it nicely to get the benefits. And if you're interested more about this, we have lectures. Juan gave a lecture last year in our computer architecture class. If you're interested, take the computer architecture class also. But this lecture you can watch if you have interest. You can see that this is the internals of a DRAM chip, actually a DRAM bank. Each DRAM bank, there are 8 DRAM banks over here, as you can see. Each DRAM bank is coupled with a processor. And you can see the pipeline. The pipeline looks kind of like the pipeline that we have seen, except it's a bit longer. And there's some instruction memory, there's some data memory, and there's some data movement engine so that you can move the data. So you still exploit locality. So a lot of the principles that we have discussed apply to this processor that they have constructed. Now, I'm not suggesting this is the best way to construct a processing in memory system, but this is one way of constructing the processing in memory system without changing the programming model a lot. And even this leads to significant performance improvements compared to existing CPUs and GPUs. And you can read about that in this paper. This paper that we wrote recently, you can find on arXiv. It was published on arXiv last month, actually, in May, in late May. And you can find out that there's a significant effort in analyzing the performance of the system here. And we compare it to, in the end, to existing CPUs and GPUs. And for workloads that are suitable for the system, and we talk about what makes the workload suitable for the system, in those workloads, there are orders of magnitude performance improvement compared to a CPU, and there are factors of improvement compared to a GPU, a state-of-the-art GPU. And there are probably benefits compared to a state-of-the-art GPU in terms of cost potentially. And you can read the paper for more details. So this is a very active area. As you can see, this is a cutting-edge paper on the topic. But there are other active areas in processing in memory on simulated systems. We also do work on simulated systems. This is another work that we have released. Again, on arXiv, you can find it freely available to anyone in the world. And here we talk about what makes a workload suitable or not suitable for different processing in memory systems. We also analyze caching. We also analyze prefetching a little bit in this particular work. And we categorize workloads. So there are actually more than 300 workloads that are categorized in this work. And we basically provide a data movement benchmark suite. Geraldo is right now working on actually open sourcing it completely. So you can even find the data movement workload suite open source soon. That's true for the workload suite that we develop to test the UpMem systems as well. Juan is doing that as well. But basically, there are really interesting things that you can do to understand why processing in memory works, when it works, how it works, and how to make it better, basically going forward. And today is the right time to do this research going into the future, because these systems need to be enabled. Okay, and the good news is industry is paying even more attention as these works start popping up and becoming more and more important. Industry is paying more attention. I mentioned this. This is at the beginning of the course. Remember, this was actually introduced in February 17th with a press release by Samsung. And basically, they're doing something similar in the sense that they have specialized units to accelerate matrix multiplication operations, let's say. And they do these operations very close to each bank in memory. And they call this, I think, FIMDRAM, function in memory DRAM. Don't quote me on that exact name. It's called FIMDRAM. I think it's function memory. Yeah, you can see that it's a function memory DRAM. And you can see that there's a 3D stacked architecture over here, high bandwidth memory, very similar to what we have seen earlier in my picture. And you can see that they're adding some multiply, accumulate instructions to be executed, offloaded to the memory side. And you can see that this is a real design, etc. I'm not going to go over it, but the good news is that real companies, big companies like Samsung, are now finally paying attention to this. Clearly, processing in memory is an old idea, started in the 1960s. When we first started working on it, it was 2011 or so. Now, finally, people are paying attention in industry, and that's a good thing, basically. The question is, of course, how will it evolve? And you can have a big say, basically, if you actually come up with good ideas going into the future. Okay, so if you're interested in processing in memory, I would recommend detailed lectures. There are many detailed lectures. And if you're interested in it, I would recommend a longer version, but an older version, as you can see, of the talk that I assigned as optional assignment. And you can find this talk over here. So one thing that I will mention is processing in memory, processing inside the device, minimizing the data movement is really important for applications that are operating at the edge, like devices like this. This is a genome sequence analysis device. You may remember it from the lecture, first lecture. And today, we don't have enough processing capability inside this device. We have to move the data out of the device. But processing in memory, processing where the data resides, is a mindset to minimize data movement in the system. And if you really want to exploit the capabilities of these devices so that we can actually do real-time analysis. For example, we give this device to a doctor, and the doctor, in a critical condition, wants to quickly get an indication of whether this patient will react positively to this drug based on their genetic disposition, plus everything else the doctor knows. And they need this information. You need to do fast genome sequence analysis, and you need to do You need to provide, you need to do some matching of a database, for example, with the characteristics that you find based on the genome analysis of this patient, so that you can make a judgment call on whether this, what kind of drug does this patient react positively to, or should not, does not react negatively to. And this is a life or death situation potentially, right? So you need real-time, fast analysis. And there may be less dramatic situations than what I described, but you still want analysis quickly so that you can move to the next phase of treatment relatively quickly. You don't want to wait 2 weeks to get the analysis results in a genome sequencer. And in some cases today, it takes 2 weeks actually. It depends on what kind of resources you get, etc., and how much money you pay also. But we want this decision to be made in 1 minute or less. And today we don't have the capability to do that. That's why I think moving data and not having enough processing power where the data is generated is a big problem. In this kind of sequencing engine, if you want to have real-time decision-making capabilities, you really would like to be able to not move the data and have processing capability over here. That's why I think processing in memory can enable new platforms like genome sequencing platforms, medical platforms, scientific platforms, etc., that can give you results in real time and much more efficiently. And we've been working on that also for a while. This is one of the papers that we have written along the way, but we've been working on it since 2011 or so, actually earlier, 2007 or so. And today, actually, we have the devices that are capable of sequencing genomes with very small form factors like this, but they're not capable of processing data. Even your cell phone is not capable of efficiently processing data. Even a data center engine is not capable of efficiently processing data. So we need to rethink how we design our systems. And if you're interested in this, we have written this survey paper. I mentioned this in an earlier lecture also, but maybe it'll become more clear right now. We're working on accelerating genome analysis a lot, and I would recommend looking at this paper, examining this paper, if you're interested in this direction. And I think this is fascinating because we can enable new applications this way and new system designs this way. And if you're interested, you can also watch this lecture, relatively recent lecture, where I talk about accelerating genome analysis and our journey in this. And there are a lot of interesting algorithmic issues also that we cover, but a lot of interesting hardware issues that also we cover over here. Okay, there are detailed lectures you can also watch if you would like. But certainly, let's conclude. I think I've given you a lot about some future-looking research. None of this you're responsible for, of course, in the exam or anything. But this is just a foreshadowing of the things that may come about maybe 10 years down the road when you take this lecture, right? Or when you look back into the field. And if you want more of this sooner, there are multiple future options after this course. We offer a bachelor seminar in computer architecture every fall and spring. And you can find web pages for all of these. They're reasonably structured. And in the bachelor seminar, I'm going to talk a little bit more about this, but we delve into particular papers and critically analyze papers, critically present papers, do brainstorming and discussion about papers. So a lot of trade-off analysis goes into it. And this is a fun seminar. We had the last seminar yesterday. It was actually live streamed. You can find some of the publicly available seminars online, and past students who have enjoyed the digital design and computer architecture course have taken bachelor seminar courses, and some of them actually are working with my research group right now, doing either semester projects, internships, experiencing an environment where they can be part of a vibrant cutting-edge group. Some of them are doing bachelor's thesis, some of them are doing master's thesis. So those are also options. But I would definitely recommend taking the bachelor seminar because that will give you a different set of skills than we have seen in this course. You will present a paper, you will critically analyze it, and you will lead a discussion about it, for example. I would also recommend taking the master's level course. This is offered every fall. It's a very project-oriented course, as we will see in a little bit. There are 5 labs. One of them is optional, and they're done in high-level language, C language, and it's fun, I think. But we're going to talk about that. And we cover a lot of more cutting-edge issues and more issues that we did not get a chance to cover in this course, clearly. You can also take, that should not be take out, I guess take our, let's say. There are also project and seminar courses that we offer every fall and spring. I have a more detailed slide related to this. If you're interested, you can also take that. And independently or together with any of these, you can decide to do research with me and my research group. As I said, we have a lot of opportunities, and I very much look forward to working with undergraduate students who are excited about doing solving important problems and who may want to have a fresh perspective to these things. I was one of them, actually. When I was doing my undergraduate degree, I did research in different labs and eventually decided to do my PhD. Certainly, this is possible as well. So you can look at our research group webpage on more about what we do, but I've given you a glimpse of it during some of these lectures, as you can see. Okay, and you can learn more about our research group. You've seen, well, at least virtually, you've seen some of the TAs. This is an earlier version of it. And you can actually read our newsletters. This is a January 2021 newsletter where we talk about some of the things that has happened in the last 1.5 years in the group. And hopefully it's interesting. It will be interesting to you. And this is the group motto designed by some of my students. And I guess this is a more newer version of this. Well, this is a newer version of this picture, let's say, that is more reflecting of the times. And hopefully we will not just have Zoom meetings going into the future. That's true, hopefully, for the bachelor's course that we're having right now. In the future, hopefully, we'll have a lot more physical lectures. That will be a different experience, in my opinion, because I don't know what you think, but I don't think this remote experience is the greatest experience because I cannot see the faces of any of my students who are in the class. And that's a bit frustrating, frankly, from my perspective, because, and also we don't have the interaction that we have clearly because you're writing your questions and I'm trying to read them, etc. So it's a different kind of interaction, which is not necessarily great. But you can read our newsletter also, as you can see over here, to get to know more about our research. And this is a little bit more about the Bachelor Seminar in Computer Architecture. Basically, it's a rigorous seminar on fundamental and cutting-edge topics in computer architecture. You get to critically present, review, and discuss major works in computer architecture. You can cover many ideas, usually with anywhere between 16 to 25 papers or so, something like that. Analyze their trade-offs, perform critical thinking, discussion, and brainstorming. Of course, you don't have to read every single one. You have to read the one, analyze the one you're presenting in a very detailed way. And there's participation, presentation, and synthesis report, and you can also register for the course online if you're interested. And I'd recommend taking it if you're excited about it, because you have the background to do it right now, because you have a basic computer architecture course right now. And then there's a master's level computer architecture course. As I said, it covers many cutting edge topics in memory, interconnects, multiprocessors, heterogeneous systems, PIM, processing in memory, and more. Many topics we could not cover in this course. It consists of lab assignments, which is actually very important because it's about 50% of the grade, I think. We wanted to make it more hands-on and lab-oriented, some homeworks and exam. And you can also find more information. You can actually watch videos. A lot of the videos I recommended to you are coming from that course. And finally, these are the projects and seminar courses. These are offered every fall and spring. These consist of short lectures and hands-on projects, which is important. It's a lightweight. These are lightweight but deep courses on specific topics you can choose from. For example, you can choose from topics in memory, and we can define the project together. If you have ideas, we're open to ideas. There are 2 courses related to memory. Storage, which is something we did not talk about as much. You can also choose them. For example, if you want to do some project on phase change memory or SSDs, it's possible. Heterogeneous computing, both programming and architectural aspects, GPUs, FPGAs, processing in memory. There are 2 courses related to this, and there's a lot of exciting research that goes on. You can program the UpMem computer, for example, or you can program FPGAs, for example. And finally, more application-oriented, but still hardware, software, co-design type of courses. And some of them actually just algorithm. You can actually develop algorithms to do better bioinformatics and machine learning as well. So these are the 2 courses over here. So there's one question. Aren't PNS courses only for ATED students? So from my perspective, no, I don't think there's anything that limits. So if you have a problem registering, just let me know. I'm happy to take courses from, take students from any department. So because I think in the end, it's a learning experience. It's a requirement for ETED students. So meaning, as if you're an ETED bachelor student, that means that you're required to take some number of PNS courses. That's for sure. If you're a computer science student, you're required to take a seminar course. I don't know if PNS courses satisfy the seminar requirement. That's good to check from your perspective. But I don't think if you want to take the course, there's nothing that prevents you from taking the course, as far as I know. And if you run into an issue and if you want to take the course, let me know, because I don't have a problem if people are excited about taking the course. I'm happy to get them admitted in some way. But again, you may, depending on what the computer science department decided, and I don't remember, frankly, what that decision is, you may not be able to count this as one of your seminar requirements. That I don't know. But you may be able to count it for some other requirement. That, again, maybe there's some room for counting it for something else. That I don't know also. That's probably better discussed with the CS department. But if you need help at any point in the process, let me know. Okay, so I think I've covered the 4 different courses that we're offering in PNS courses. And again, if you have questions, let us know. And you can find the description of the courses and some of the lectures that we presented online as well. But we don't put out all the lectures right now. We're going to put out more lectures related to them, but we didn't do that yet. Okay, so doing research, if you're interested in learning more and doing research in computer architecture, I have 3 suggestions. I've actually presented the slide right before the systolic arrays lecture also. Feel free to email me with your interest. Please CC Juan. My email tends to be, unfortunately, extremely unreliable. I get too much email. Maybe I have, essentially, I'm not operating in a very good point in my email latency curve, let's say. The load of emails is too much in a sense. So if you CC other TAs that you're familiar with, Juan being a primary one, that's a very good idea. Because if I forget, hopefully they will not forget. And you're also always welcome to email again or find me in different ways as well. And I would also recommend taking the seminar course or the computer architecture course. That goes without saying. And if you're interested, hopefully you're doing some readings and assignments on your own. And I know some people in the past have done a lot of readings and assignments on their own. And as I mentioned, there are many exciting projects and research positions, memory systems, and I'm not going to go through this again. Basically, I've already said this, and we've covered a lot of really interesting things in the lectures. And a limited list of project topics is in this thesis page, but don't take this as a comprehensive list. Basically, my group works on all aspects of computer architecture and a lot of the topics that we discussed. Thesis topics may be some things that we have envisioned, but you can also define your thesis topic if you work with us. And we may also have other thesis topics that are not exposed on our webpage as well for various reasons. Just one reason is there's just not enough time while doing research to write up a thesis topic online. But if you're interested in architecture, definitely get in touch with us. And again, I think this is a guideline of how to do projects with us. The biggest part is be excited about the topics that we work on and be excited about generally in computer architecture. Have a good mindset. Everything that I said earlier applies. Have good goals and get in touch with me and my students postdocs. And you can, again, you can do other things over here. Hopefully you've taken our course and enjoyed it, one of them at least. You can browse the projects, read our papers, and get in touch with the authors. Maybe you've done some of that. I don't know. If you're interested, for example, you can read the RowHammer paper, any of the RowHammer papers that we have written. And you can also email us, certainly. And you can also optionally apply. We have a formal application site. But if you're an ETH student, it's easier to contact us, especially if you have taken our courses. You have a more or less personal relationship with us. But outside students who are not part of ETH, we definitely ask them to apply because we do not know enough about them, right? But if you've taken a course with us, especially the seminar course, we've interacted with you a lot more. In a course like this, the DCA, and very unfortunately, because of the Zoom-based nature of the course, online nature of the course, we do not get to interact much. And the course is huge also. There are many students. But if you take the seminar course, we interact a lot and we get to know you a lot better. And you get to know us a lot better. It goes both ways. And then you don't necessarily need to apply through our official page. But if you're applying from the outside, for example, if you're, I don't know, living in some other country, and if you want to do research with us, you should definitely apply and let us know that you've applied. Okay, so I'm going to end this lecture and class with 2 quotes that I like. Actually, there are more quotes that I like than 2, but I think it's good to be concise. Just talk about these 2 quotes. But before that, I think I will handle this question that I just saw. Okay, this is a question. It's a long question, I see. As a programmer, it means that some people are still here. That's good. This is completely optional part of the course. And if you're still here, that's good. I think that tells me that you're interested. But basically, the question is, as a programmer, we always assume our instructions to run correctly. But if any tiny needed part of the ones we looked at fails, we get wrong results. Are chips nowadays reliable enough that this doesn't really happen? Or are there extensive hardware mechanisms to handle those errors? And if so, how can that be done? It's an excellent question. And I think the answer is we don't completely know. Why we don't know? Because sometimes faults happen. And sometimes it's because of hardware problems in the chips. And there's a good fraction of the faults, hardware faults, that lead to some incorrect execution in the programs. It could be RowHammer, one example, right? It could be there's some issue in the ALU that's exercised only under some conditions, some operating conditions, some alignment of the instructions in some way. These things happen, and it's not completely possible to perfectly debug every single hardware component in our systems today, because it's complicated. And you saw that we have trillions of transistors, right, in our chips today. So basically, we don't absolutely know. There are some faults that actually lead to crashes, etc., just because they're hardware faults, and you cannot basically blame the software for it. Clearly, there are a lot of faults where you can blame the software. I'm ignoring those, but these are hardware faults. And for example, when I was at Microsoft, there was this study that was being done at that time. I think they eventually published the results. Maybe I'll try to find the publication, where they showed that at that time, the Microsoft Windows had the blue screen. I don't know if Microsoft Windows has this blue screen, but this was a famous blue screen. Whenever you get an error, you saw a blue screen and you had to reboot your computer. Nobody wanted the blue screen, clearly. But there was a study that was done at that time that showed that about 10 to 15% of all blue screens are due to some hardware problem, hardware fault. And some of the hardware faults could be preventable. Some of the hardware faults may not be preventable. One way to prevent the hardware faults is, for example, have error correction codes inside the chips. In DRAM, for example, people are adding error correction codes today, but it's not easy, or it's not enough to protect against all faults. For example, error correcting codes is not enough to prevent RowHammer type of vulnerabilities, RowHammer type of faults. So it really depends on the type of fault that's happening, the design of the hardware. And some of these faults may not be reliability issues. Some of them may be logical bugs, right? The hardware is designed in some way, and humans are designing it. There could be logical bugs. Some of them could be manufacturing reliability issues. So there are all these different kinds of things. We have analyzed, for example, in a paper that we published in Micro 2008, we have analyzed hardware bugs. And we've seen that the microprocessor errata is increasing. It basically has even more errors that are documented in the instruction manuals, in the architecture manuals, that basically shows that microprocessor designs have increasingly more bugs. And sometimes these are exercised. So I think your question is very to the point. It's very important. There are reliability issues, there are logical bugs, etc. And they're all intermingled when you get an error. And you need to basically tease out what is happening when you get an error. And sometimes it's not easy to do. That said, I think people are doing some studies. Actually, there's a paper from Google in this Hot OS. There's a workshop that has happened. It's called Hot OS, Hot Operating Systems. And Google basically shows in this paper that there are a lot of faults that happen in hardware that lead to basically some corrupt execution in software. I'd recommend finding it out. And hopefully my TAs who are listening will find out right now. You can feel free to put it on the chat if you find out. But this just happened a couple of days ago. And these Google folks basically analyzed the hardware and the software that they have. And they showed that there are a lot of hardware faults that cause their software to crash or become corrupt in some way. So these are real, basically, and they're going to become worse going into the future. And essentially, the answer to the second part of your question is, are there extensive hardware mechanisms to handle those errors? And I can confidently say that the answer to that is no. Basically, unfortunately, there are no extensive hardware mechanisms today to handle all types of errors. Some type of errors, for example, memory has error correcting codes, not all memory. Consumer memory in your laptops, for example, don't have error correcting codes. Increasingly, they're going to in the future, but not enough error correcting codes. They can correct, for example, single error corruption. They can detect double errors. Well, not always. In some cases, they can detect double errors, but not always. So they're limited. If you have 3 errors, for example, in memory, you're not going to be able to correct them or even detect them in some cases. So certainly there's a lot more to be done in research as well to understand the causes of these faults and to correct them. But your question is a good critical thinking for sure. Okay, so there's another question. That's good. We were also having probabilistic algorithms this semester. Are ideas of probabilistic speed up or also implemented in hardware apart from ML accelerators? So that's a very good question also. So ML accelerators certainly make that trade-off, right? Basically, so it looks like I think one of my students, Max, who's doing research with us, actually posted the Google paper, cores that don't count, and I would recommend looking at that. Thanks, Max. Let me go back to answering the question. So ML accelerators, for example, because things are approximate today, and machine learning by nature is probabilistic, you can cut corners in hardware and not have highly accurate representations of data, for example. And you can basically omit some computation. That's possible. You can make the computation simpler, cheaper. You can, for example, instead of using 32-bit floating point operations, you can use 4-bit integers. In fact, inference engines today use 4-bit integers. That's one way of approximation, for example. And I would, maybe if you stretch it, it's not necessarily a probabilistic algorithm, but it's taking advantage of the probabilistic nature of the algorithms that are employed in the machine learning, statistical nature of the machine learning. And certainly machine learning accelerators take advantage of it. As far as I know, in the general purpose domain, this is much harder, right? You need to know your application. And I think there's another place where this is taken advantage of, which is video. For example, when you have a video accelerator, depending on the bandwidth you have to the network, for example, the video accelerator, both software and hardware, can scale how much processing they do to the video, depending on the battery life also. So your video accelerator can work faster or slower. So this is taking advantage of the fact that video is also, I mean, in some sense, probabilistic from the user's perspective, right? If I don't see every pixel correctly in my screen, I can still make sense of it. Especially when I'm running out of battery, maybe I would prefer my battery to run 1 hour longer than seeing everything perfectly on my screen, right? So you can make this trade-off. So on an application basis, this probabilistic nature of the algorithms and also tolerance of the users to the probabilistic nature can be exploited. And I think machine learning accelerators, video accelerators are the places that I can give you examples of, but this is much harder to do in the general purpose domain, because in general purpose domain, again, you don't know what algorithm in the real true general purpose principle, you don't know what algorithm you're really executing, right? So you cannot customize. But I think increasingly the stochastic or probabilistic sort of acceleration is going to be employed as applications become even more stochastic and stochastic. But again, you cannot really generalize it to all applications. I mean, if you want to generalize to all applications like banking, it's going to be difficult, right? I would prefer that probabilistic nature of the hardware or the algorithm to be in the favor of my bank account. But if it becomes either way, it's going to cause problems. But that's a very good question also. Okay, there's one question that I think is on YouTube. What is your view on analog compute? Are we constraining ourselves by converting everything from analog info to digital and backwards, similar to a process-centric architecture? So this is also an excellent question. And I think, again, we should really be examining very energy efficient forms of computation going into the future. And so far, we've been completely digital, especially in the general purpose computation domains, right? And I think going forward, we do need to think about analog computation. Yes, that was not the case. In the early 50s, 60s, 1960s, 1950s, there were analog computation computers that were designed. But over time, people developed the digital abstraction or became more comfortable with it. And digital abstraction was a lot easier to deal with, of course, because analog is you're operating in the analog domain, right? And while the nature is completely analog, no question about that, it's also subject to noise. Basically, you're very much subject to noise whenever you do some analog computation. And people are moved to digital so that they can avoid these noise type of issues and they can get better precision, let's say. But I think going forward, we do need to re-examine this choice. Maybe we don't go completely analog, but there are cases where we can benefit from analog computation capability to a limited extent. And maybe we do the digital to analog conversion and analog to digital conversion not as often as we do right now, because today everything is converted to digital right away. and we operate on the digital domain. And clearly, the digital domain is not scaling very well. But if you operate on the analog domain, in fact, you can use the memories for computation. That's what I mentioned earlier when we talked about processing using memory. A lot of the processing using memory work takes advantage of the analog operational principles like chart sharing principles in DRAM, but other analog operational principles like current laws, like Ohm's law, which is an analog law, to really do the computation in the analog domain. And I think people have shown that this is very efficient. The difficulty is whenever you need to convert it to the digital domain, it's at some cost. But if you actually design your system carefully, you can take advantage of both analog and digital. And analog is certainly it also rhymes well, if you will, with the stochastic nature of algorithms today, right? If algorithms are stochastic, and if analog is stochastic, subject to noise, maybe you can get away with it, right? So machine learning, for example, can again benefit from analog computation. But I think analog computation is more general. You can more general purpose because if you can do limited analog computation, limit your error, limit your noise, and you can benefit significantly from the energy efficiency of analog computation, you can have a much better system. So going forward, I think, yes, certainly this is something that needs to be rethought. So somebody on YouTube says analog is useful for AI. Yes, absolutely. And data converters are expensive in terms of power and area. That's absolutely true also. Basically, any sort of conversion that you have, analog to digital, digital to analog, is going to be expensive. But if you actually do it in a judicious way, in careful places, then you can actually get the best of the analog while minimizing the conversions. This is also similar to optical computing, right? We did not talk about optical computing, but that's a subject of, again, future courses, lectures, research. If you have optical transmission, optical interconnects, for example, the question is basically, do you do optical transmission or electrical transmission? And people have shown that optical transmission is very efficient, very high bandwidth. But electrical is how we do things today, right? But today's computers are electrical. They don't do optical computation. People also looked at optical computation as well. There are some overheads. But do you do communication optically and then convert the optical data to electrical data when you want to compute on it? And people have looked at the trade-offs. If you have a very costly optical to electrical and electric to optical converters, there's a danger, right? You do communication optically, and then you need to convert into the electrical domain to do the computation, and then you need to convert it back to the optical domain to do the communication, etc. Then you may actually lose. If you're very careful, maybe you gain. But if you also move the computing to the optical domain, if you have optical computation and replace the electrical transistors, and then actually it becomes interesting as well. But again, that's beyond the subject of this course. And actually, it's a lot of it's subject to research. How do you do the computation optically? Okay, is there research to store information optically? Yes, there's also research to store information in many different ways. Optical is one example. Unfortunately, I mean, they're not completely there yet. So there is storage elements. So certainly we have a lot of good storage in terms of magnetic storage, right? So magnetic storage is great in tapes, for example. Solid state drives are great, but optical storage has not been cost effective yet. But going into the future, again, things can change, right? There are a lot of emerging technologies that people are examining. For example, there's work in Microsoft in Cambridge that tries to store information in glass. Now, it's not clear if this is going to be very fast, but it's going to be very durable. There is also research that tries to store information in DNA, but that's going to be very, very slow unless we are extremely successful in our research, for example, to try to accelerate genomics, so genome analysis. So there are many, many different storage media that people are examining. Unfortunately, none of them are good enough to make a dent in the memory hierarchy today or the storage hierarchy today. They're still subject to research, which is good to do, of course, right? There's also research on quantum that we briefly discussed, which is even further into the future potentially, even though there's a lot of investment into it. Quantum principles are potentially even into the future. And certainly quantum storage is not clear. The current state of research in quantum computing, even quantum computing considers DRAM, for example, as their main memory. And that says something about DRAM and how successful it is, I think, going into the future. How successful our current technologies are. It's very difficult to disrupt them unless you come up with solutions to a lot of the difficult problems that these other technologies have. But that's why they're research. That's why research is very important to do, so that at some point you can disrupt the systems, right? Just like phase change memory disrupted systems. We talked about phase change memory. We talked about the research we have done and research others have done. Our research started from 2007, and we wrote the first paper in 2009 saying we should replace DRAM with phase change memory. And that sort of memory came about only in 2019, right? And this is phase change memory. This is a technology that we knew about a lot in the past. We just needed to make it happen in some way. And that required a lot of device level, circuit level, chip level research, plus architectural level research. But optical, quantum, these are even into the future. Glass, these are even into the future. And DNA, I think we'll see, I guess. Okay, very good questions. I think I will conclude with these two quotes that I like. As I said, there could be many, many other quotes that can be given, but I will be concise. I like these two quotes. These are from someone who has received the Nobel Literature Prize. You may know this person, but I like this quote because this is nice. The reasonable man adapts himself to the world. The unreasonable one persists in trying to adapt the world to himself. Therefore, all progress depends on the unreasonable man. In a sense, this says basically you should be critical of how things are done and what's happening so that you can actually enable progress. And hopefully, but of course, I think unreasonable man needs to have a good mindset with something good in mind. And unfortunately, there needs to be a moral judgment over here as well, because if the goal of the unreasonable man is to destroy the world, then you have a problem, right? But this is said in a way, assuming goodness of the unreasonable man over here, if you will. So I think this points to the critical thinking. And I think one of the most harmful ways of thinking in the world is this sentence, but it's always been done this way. So basically, just because things are done in some way doesn't mean that that's how they should be done that way, right? There are many reasons why things are done that way, and that's not necessarily the best way. It's all a trade-off in the end. And sometimes the trade-offs become extremely negative to the way things are done. And whenever that happens, you should realize that immediately and change. And this goes well with the other quote from this person. Now I've revealed that person, George Bernard Shaw, who's an Irish playwright and novelist, actually. But this ties in nicely with the second one. Progress is impossible without change. And those who cannot change their minds cannot change anything. And basically, I believe this. If you're too resistant to change, or if you're resistant to change, then you cannot really do anything big. And I hope you as takers of this course will remember these quotes, because I think these tie well with each other. As I said, one of the harmful things that has been against progress has been, oh, but we always have done it this way. And whenever you hear that, you should perhaps be very critical. Oh, but this is the only way to do things. Hopefully this course gave you many, many other examples of different ways of doing things. And that's really the mindset. If you don't take away anything out of this course, I would suggest taking away that mindset. Basically, there are many ways of doing things, and it all depends on the trade-offs. And you need to find the best way of doing things depending on the requirements and the conditions. And be the unreasonable man with a good mindset and be open to change all the time. Okay, and that's how I will conclude. I think there is a lot more in computer architecture that we're not going to cover, and we're already out of time. For those who have stuck around, thanks. But for those who have not, you can also watch this if you're really interested separately. And hopefully your next lectures, next semester in your career is going to be in person so that you can get the benefits of it. But hopefully you can also have the flexibility of watching them online. And we will certainly try to provide the best of both worlds because different approaches work best for different people, as we have discussed in the past. But I think the lack of an in-person classroom certainly I understand it's not good for many of you. And believe me, it's not good for me also, because I really don't enjoy lecturing to my beloved iMac over here without seeing your faces. But anyway, hopefully we'll change that. But I think you can be the agents for change also for that. Get vaccinated, hopefully. Okay, I think we're done. Are there any burning questions on anything? I know we're way out of time, but some of you are sticking around, and feel free to ask questions. Okay, I guess I don't hear or see any questions. I think with that, at least we're done with the lectures. Hopefully I will see some of you in person in future semesters, and maybe during the exam, because that is planned to be in person at this time. Don't worry about the exam, worry about learning, and we will be in touch with some material that you can study for the exam as well in the remaining, well, during the summer months. But apart from that, hopefully you will enjoy your summer, and you will get some time to rest as well as grow at the same time. Okay, I think we're done. Thank you. Thank you for everyone who's saying thank you. I cannot respond individually, but I can see it right now on the screen. I think good luck with everything. Feel free to contact us. As I said, feel free to email me and the TAs regarding anything that you want to talk about. And we will be in touch regardless about the exam at least. Okay, take care. Have a good summer. And have a good weekend before that, of course.